Hi, in this video we'll go over unit testing. The software testing lifecycle consists of different types of testing, with unit testing being the very first one that's usually done, followed by integration testing, and then it's system testing and acceptance testing. So today we'll focus on unit testing in this video. Now, when should you write a test? So traditionally it has been written after the source code is written. So first the program is written and then the corresponding tests are written. But in the modern with agile processes and with specifically extreme programming, things have changed, and there is this methodology called test driven development, where the tests are written first and then the actual program is written. So the way that works is, the very first thing that happens in the cycle is a test is added. Depending on what functionality is being developed, a test case to test that functionality first gets added. And then the test is run through automation. So there is a way to run all of the tests that are set up in the test suite, and those automated tests are run, and the idea is to see this new one fail, and the reason it would fail is because the functionality corresponding to that test has not been developed yet. Then the next step is to actually write the code to develop that functionality or that function or method, and then rerun the automated tests. And this time, if the functionality has been written correctly, then the test should succeed. Well, if it doesn't succeed, then we have to go back and rewrite the code, fix the code, and then run the automated tests again. And then in the cycle, if any even if the tests succeed, sometimes we might have to refine the code, refactor the code. So basically we refactor the code and then again go back to running the automated tests. So the idea is to add a test, then write code, make sure that the tests succeed, and then again go back and keep adding new tests, new code corresponding to those tests, and make the tests succeed. So that's the idea with the test-driven development, and the modern software development processes are more and more moving towards this kind of development. So now we'll focus on unit testing specifically. So this is the life cycle of testing. So we want to start specifically at a single unit first, and that's what we're focusing here in unit testing. We want to test individual units first, and then we'll move into a bigger subsystem and then the whole system and so on. So unit testing can be done at different points during the development of the program. It could be done at compile time, and that's basically static testing. So here the some code has been written, it may not be complete, it's still not built and it's not being executed. Even as early as that, at that stage, we can perform unit testing. So some of the different ways in which it could be done. The first one is through a static analysis of code. So we basically look at the code and analyze it at compile time, but just by reading it, and that can be automated through certain tools as well. And what we're looking for is any kind of anomalies or bugs that can be caught at that stage. A second way to do it is through reviews. This can be done either through a formal process or informally. It's always a good idea. So the reviews again can be done at two levels. It can be done at a personal level, wherein, or an individual review, where a programmer reviews his or her own code by looking through the code, reading through the code, and walking through the logic and making sure the logic makes sense. The other one is a peer review, or this is where the review is done by someone else, maybe a team member or a team as a whole. And it could be done informally through walking through the code and walking through the logic, or it could be done in a more formal way through code inspection, and again a number of tools support it as well, wherein this is basically, the idea is that Any new code that is written must pass through, if a formal process of code inspection is followed, then it must pass a review by another member from the team to make sure that there's no logical errors, there's no initial bugs or anomalies found in the code. It also helps with good design practices and making sure that good algorithms are used for efficiency and performance. So that's reviews. And then the third technique is using automated tools. This is where one can check for any kind of syntax or semantic errors through tools. There are a number of tools, and we will discuss those briefly. The idea is that they'll statically look through the entire code, parse through the entire code, and report on any syntax or semantic errors. Coding standards could be checked, coding guidelines can be preset in these tools, so that if all of the developers in the team comply with those guidelines and follow those guidelines. So we will look at a few of those tools. So basically this is static testing that's done at compile time. Dynamic testing, this is done at runtime, so this is when the program has been developed fully and it can be executed. And at that time, a number of tests could be run to make sure that the results produced by the program are what is expected. So at runtime or dynamic testing, again, there's two types: there's black box testing and white box testing, and we'll go over these two techniques today. So we'll start with the static analysis tools. So the first one is, you would have, if you've used IDE like Eclipse or NetBeans, you've probably seen this already, where compiler warnings and errors are generated by the IDE as you are typing in code. You don't even have to hit the build button to be able to see these warnings. It's displayed as you are typing in the code. Some of the common ones that you see are probably, if you're trying to use a variable that has not been initialized, then it'll throw an possible uninitialized variable error. If there are empty blocks, if there is no documentation, those kind of things are reported. If you're trying to use some kind of objects that are associated with checked exceptions, if you use methods associated with it, then the compiler throws an error saying that you have to check for exceptions. If the assignment has no effect, it's going to throw an error about that. So, and any of the compiler errors, say if the syntax is wrong, then the IDE is already reporting those and indicating them in the red with the red mark, and providing some hints and possible fixes in order to fix it. So that's all of that is happening through static analysis, and the focus there is to look for syntactic errors and provide with those warnings. Some of the other tools, CheckStyle is a tool that helps with code guideline violations. So there is a way to customize the tool and set the guidelines up front, and then it looks for any code guideline violations. So some of the things could be, what should your tab space look like? What should your indentation look like? How should your blocks be? Where should the the begin brace, do we want it at the end of the statement, or do we want it at the beginning of the next statement, and so on. So those kind of guidelines can be specified, and CheckStyle will look for it in the code and report on it. So CheckStyle can be, it's available on sourceforge.net. There's the URL for it. The next one is find bugs, and find bugs helps with finding code anomalies, any kind of well-known anomalies which are likely to cause errors if we continue having that kind of code in your program. So those are the kind of things that find bugs will find and report, and it usually also provides some kind of a warning level of how severe it is and how important it is to fix it. Again, customization is possible depending on what kind of things are treated as anomalies in your project. The tool can be customized so that it reports only on those that you consider are critical for your project. So some of these anomalies could be, say, using an object that has not been initialized, that is null, and if maybe it will get initialized somewhere else later on in another method, but it does the reporting and warns the users on it. And like I said, customization of these anomalies is possible. It provides a list and one could check or uncheck what needs to be checked for. The last one is metrics. And the purpose of this tool is to look for structural anomalies. It basically provides a lot of information about the entire overall structure of the program, the number of classes that are in there, the dependencies between classes, and the number of levels of dependencies. Basically, it provides a visual representation of the entire structure, like it's shown in that figure. And a lot of times looking at this visualization can help understand the overall structure of your software and fix any issues or anomalies in there. Again, metrics is also found on SourceForge. All of these are available. They're also available as Eclipse plugins specifically for Eclipse IDE, so they're very easy to install and use them in your projects. So those are some of the static analysis tools that are very useful at the unit testing phase. The next one we'll look at is black box testing, which is one of the dynamic testing technique, and it's done at runtime. Now, as the name indicates, basically black box testing focuses on testing the application without worrying about the inner workings or the inner details of the application. So it doesn't matter how it has been implemented, what kind of data structures or algorithms are used within the application. The tester, as a tester, all one is concerned about is what are the inputs for the application. What are the inputs that I need to provide to test this software or this application? And what are the expected outputs from it? And are we getting those outputs or not? That's pretty much it. So that's the focus with black box testing, and it's the entire unit that's under test is being treated as a black box, wherein the only information that's needed is the interface information. What inputs do I provide, and how do I invoke the functionality that I'm interested in, and what is the result that's produced. None of the internal aspects of the application are needed, or there's no need to understand that in order to do the testing. So that's black box testing. The focus is on that I/O behavior, the input-output behavior. So the test cases are created with different possible inputs and the output, the desired output for each of those inputs. And the idea is that this component should pass all of these tests. So with black box testing, we typically require what's called a test oracle. So a test oracle is basically a strategy to determine if a test passes or fails, which means in some cases, we need to know what is that desired result, and we need some kind of a strategy to compute the desired result first of all, and then compare it with the results produced by this unit that's under test. So test oracle is basically that strategy of coming up with or determining whether a test has passed or failed. So our goal with black box testing is we want to be as thorough as possible, and we want to test this unit as thorough as possible. But then at the same time, testing takes time. So we want to reduce the number of test cases. We want to be effective. We want to be effective with our testing and test all possible cases, but then at the same time, reduce them. And the way it's reduced is by coming up with equivalence classes of test cases, so that we can we can use one test case from each equivalence class and test for it. So this technique is called equivalence partitioning, and we'll look at a few examples of this. So the idea is to analyze the inputs and then divide them up into different equivalence classes, so that we can choose one test case from each equivalence class. So the general guideline, again, there's only guidelines with testing. There's no rule book, and It's not that if you follow the rule book, you've done thorough testing. There's guidelines, and then the rest is up to the creativity of the programmer who's doing the testing. So the first, in order to come up with equivalence classes, the first type of input that we'll look at is a range of values. Say the input that you need to provide to a unit that's being tested is, the possible input is a range of values. Say you can provide a range of values from 5 to say 1200, the numbers from 5 to 1200, and I just made that up. Now typically whenever you have a range of values, then there's 3 equivalence classes that you can come up with. The first class is below the range. So basically you choose a value that's below the range, so something that's less than 5. Then within the range, so one value from between 5 to 1200, including the 5 and 1200. And then the third one is above the range, so a value above 1200. So that way, so those are the 3 equivalence classes. So you've now tested for 3 different types of inputs that are representative of this range of values. So now our goal with the test cases is to use inputs that are valid, and then we also want to use inputs that are not valid and make sure that the tests fail for that. So that's the expected behavior for those non-valid values. So we always have to test with values that are not valid, the edge cases, the base cases, things like a test for 0. So say you have to pass a number as an input. It's always a good idea to test for 0, test for a negative number, and then test for beyond the maximum number that's expected. So those are the kind of those are the general guidelines when you're testing, when your input is a range of values. The second kind is when the input is from a discrete set. It's a member of a discrete set. So basically you have a discrete set of numbers. I'll just make some up here. Say the input, a valid input would be one of these numbers from this discrete set. So in this case, there's 2 equivalence classes, basically a valid discrete value. So pick a value from this discrete set, and then invalid discrete values, which is pick a number that's outside, that does not belong to that discrete set. So there's not much over there. Now if it's a small discrete set, like in this case, you can test for all of the cases, but then that's not always the case, and then our goal is to reduce the number of test cases so that the testing can be completed in a reasonable amount of time. So again, like I said, there's no rules, they're all just guidelines. Here's another example. The class shown is a calendar class. It's called My Calendar, and the purpose of this is to simulate a calendar. So it has a function in there. There's a method called get number of days in a month. So basically the purpose of this method is it takes in any month and a year and computes the number of days in that particular month of that year. So it needs to do that calculation. So say we have this method, say the implementation has been done. Our goal is to come up with test cases to test this particular method. So, so let's see what is the ideal number of test cases. So what are the different equivalence classes that we can use in order to do this testing. Now, to give you some more details about the representation, the month is taken in as an integer. So the valid values would be the numbers from 1 through 12, because 1 represents January, 2 represents February, and so on, and 12 represents December. So the set of valid values for that first input month is this range 1 through 12. Then we have our second input is year. So and the representation for year is basically a 4-digit number like 1904, 1999, 2000, 2018, and so on. So with that said, like our goal is to now come up with the test cases, the ideal number of test cases with which we can thoroughly test this method, get number of days in a month. So let's walk through this. Now, let's assume that this calendar is a Gregorian calendar. So we are going to use our knowledge of the Gregorian calendar in order to come up with these equivalence classes. So our first, we'll analyze our first input, which is the month. Now typically our months have either 30 days or 31 days, with the exception of February, which is 28 days, and again with the exception of in a leap year it's different. But anyway, when we are looking at the month, we basically want to make sure that the method is doing the calculation correct for the 30-day months, for 31-day months, as well as for February. So those are the three classes from the valid values set. And here now we are not just blindly applying that it's a range, so we'll test for one value less than the range, one value within the range, and one value greater than the range. We'll still do that, but again for within the range we'll have to use some of our domain knowledge about calendars, and that's where this comes. So we are going to test for the 30 days, 31 days, and February. So that's from the valid values set. Then in addition to that, we want to check below the range. So our valid values is 1 through 12, right? So we want to then check for below the range, which will be like a no month. 0 is a no month. It's a edge case, and it's invalid in this case. Then we'll check for 13, which is outside of that range, greater than 12. And then it's always a good idea to check for -1 as well. So there we have 1, 2, 3, 4, 5, 6. We have 6 test cases based on the first input. So basically for these 6 test cases, we pick one input each. So we'll pick a month, a number that represents 30 days, say April, so we pick 4, then pick a day with 31 days, say January, and then pick a month with February, so that's the number 2, and then we'll pick 0, 13, and -1. So those can be our different test cases to test different kinds of months. Now in addition to this, now we also have to look at our second parameter, which is year, and what values we can pass for the second parameter. So again, thinking of the equivalence classes for years, so we'll always check for a valid value, a normal kind of year. So that's our first equivalence class, a normal year. Our second equivalence class is a leap year. So there's leap years, and whenever there's leap year, February is treated differently. So we'll have to check for those and make sure that the function is doing the calculation correctly. Now, so leap years can be those that are divisible by 4, not divisible by 100, but then they can be divisible by 400. So that's the rule to figure out if a particular year is a leap year or not. So we want to make sure and test for all of these 4. A leap year that's divisible by 4, that's a year that's divisible by 100, that should not be treated as a leap year, and a year that's divisible by 400, which is treated as a leap year. So there again we have those 3 different test cases for leap year. Then we want to test for the years before Christ, so like a -200. So that's another test case. And then year 2000, that was the millennium when 2000 came about. There was a big issue with the number of software systems. So with software systems, we always like to test around 2000. So before 2000, at 2000, which is 2000, and after 2000. So there we have three more test cases. So basically, again, if you do accounting, there's 1 here for normal year, 3 for leap year, and then 1 here for before Christ, and then 3 over here for at 2000, before and after. So now if we sum up all of these, we get about 12 different test cases. So and then that's with having done that, we can be reasonably confident that we've done thorough testing of all possible cases of inputs. And the reason we are doing this is we want to make sure that this method, get number of days in a month, is doing the calculation correctly for all of these cases. So that's the idea of equivalence partitioning, and that's how test cases, different possible inputs are generated for the test cases using this equivalence partitioning technique. The next technique we'll look at is white box testing. So far we discussed black box, wherein we are not concerned about the inner workings of the application. We're just using the interface information, what's provided and what's the desired result, and is the component, the unit being tested, producing those results or not. With white box testing, it's the other way around. Here we focus and go deeper into the code, and we focus on the inner workings of the code. So the knowledge of the actual program is being used over here in order to do this testing. So typically white box testing should be done by the programmer, or at least a person who has knowledge of the program, because they need understanding of how the algorithms and the data structures that have been used for the development of the component. So, so this is not just about the user interface anymore. So there's different ways in which white box testing is done. Now, one of the typical things that's done is unit tests are written using all of the black box techniques that we already discussed, and then through white box testing, code coverage is calculated. So what I mean by code coverage is, through the tests that were written, how much percentage of the code was actually covered. And there are a number of tools that provide these kind of reports. One of the popular ones is ECL Emma, which again is available as a plugin to Eclipse. It can be installed along with Eclipse, and whenever automated tests are run, the code coverage report also can be run to see how much percentage of the code was covered. Now, when we look at code coverage, there's different types of coverage. How are we looking at this code? Are we just concerned about statements that are written and their coverage? So that's called statement coverage. Or are we looking deeper and looking at the different branches, and are we interested in if all of the branches are covered or not? That's branch coverage. Then there's condition coverage, if all of the different conditions are covered. And then there's path coverage. We can generate all of the different paths through the program, through the entire program, and if all of them are covered or not. So there's different levels of code coverage that one could look at. And like I said, here now we're using all of our knowledge of the actual inner workings of the program in order to analyze the code coverage and come up with, so basically if we feel that the code coverage is not enough, then more test cases will have to be written to make sure that those lines of code that were not covered get covered. So we look at this example of a method called return input. I mean, this is just a dummy method for us to understand these different kinds of coverage. So return input takes in 4 arguments. The first one is an integer. It's an integer called input, and then the remaining 3 are Boolean values: condition 1, condition 2, and condition 3. And this method returns integer as the output. So inside of the method, you'll see that there are 3 if conditions. If condition 1, do something; if condition 2, do something; if condition 3, then do something, and then finally return y. So that's how the method is written. Now say we have a test case wherein we are passing a number x, it's some integer x, and then for the 3 conditions we're passing true, true, and true. So let's go back to this method and see what kind of coverage will we achieve. So basically what we're passing, the test case, our first test case is x, true, true, and true. So these are the values, this is the input that we are passing. So basically with this, what will happen is on executing this method, our the first statement will get executed, wherein whatever is passed in x will get assigned to our variable x, y gets initialized to 0, and now I'm marking on the left hand side, I'm marking all the statements that are getting covered as a result of this test case. Then we get to this statement. It says if condition 1, our condition 1 is true, so the condition holds, so it's going to enter into the if loop and increment x. Then it goes to the next if condition. This is also true, so it's going to enter the condition and decrement x. Then the third if statement is executed. Our condition here is also true, so whatever is in x gets assigned to y, and then there's the return statement, so y gets returned. So as you can see, all of the statements in this method got covered. All of them got executed, which means all of them got tested. So there's 100% statement coverage with this single test case. So that's called statement coverage, wherein we are just looking at the statements and if all of the statements in the method got covered or not. Now let's look at another test case. Now so that was statement coverage, but then if you think about it in terms of branches, we'll see that only half of the branches were covered. And the reason for that is all of our if, there were three if statements, and in all of the three if statements, the true branch was the one that got covered. So only half of the branches were really covered with that first test case. So if we look at the branch coverage, what we got was only 50%. We only got a 50% coverage if we look at this in terms of branch coverage. So in order to achieve 100% branch coverage, we'll then have to add another test case. Say if we add the test case x, false, false and false, then that will take care of the other branch, right, the failure branch. So we took care of all of the true branches. It will take care of all of the second test case will take care of all of the false branches, and that way we can get 100% coverage. 100% branch coverage with two test cases, and the two test cases are the first one with true, 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 and then the second one with false, false, false. Okay, so statement coverage could be achieved with just one test case, but 100% branch coverage, in order to achieve that, we need at least two test cases. Next, let's look at path coverage. Now, if you look at all of the different paths that are there in this program, so here's this tree here shows the different paths. So here's our first the entry point, the first if condition that we had. So that's our first if, and then based on whether we enter the true side, the true path, or the false path, we could be on either side of this tree. And then at this level is our second if, and again there could be two paths from there, a true or a false, and the same thing on the other side. Our first if condition could have been false, but then the second one, depending on whether it's true or false, we could either go this way or this way. And then here's our third if. So so basically you see that there are 8 separate paths in that entire for that particular method that we're looking at. And so far we tested for 2 test cases, the true, true, true case, and then the false, false, false case. So those are the only 2 test cases that we have covered for so far, which means in terms of path coverage, what we have is only 25% coverage, because we only covered 2 out of the 8 paths. Now, how do we cover? How do we achieve 100% path coverage? We basically have to have 8 test cases with all possible combinations of the booleans that need to be passed. So, if we test for all of these other cases, then that's when we can achieve 100% path coverage. So with white box testing, basically these are the kind of details that are looked at, and depending on what the testing goals are and what kind of coverage we want to achieve and how much coverage we want to achieve, the test cases are generated based on that, and additional test cases might have to be added beyond what was done with black box testing. So in general, unit testing heuristics, the set of rules would be, the procedure is you start out with creating unit tests, and typically it's done when the object design is completed. The object need not be implemented yet, but the object design is completed, which means we know what are the attributes of the object and what's the behavior of the object. At least that much should be known. That's when we can start creating unit tests. Then we use black box testing to test the functional model. So we basically use the information about the functionality of this unit that's being tested, and based on that generate the test cases. Next, we can come up with more detailed test cases based on white box testing, and further add to it. So with white box testing, we're basically testing the dynamic model now. With black box testing, we're really testing the functional model because we're looking at just the interface information. But then with white box testing, we can test more of the dynamics of the program. Then once we have come up with what those test cases, what the unit tests should be, then we actually develop the test cases. And we want to also make sure we have an effective number of test cases, not too many, not too less. It has to be the right number to ensure that we've tested the unit thoroughly. So that's where we use the equivalence partitioning in order to do this. Next, we want to cross-check and eliminate any duplicates, because we don't want to waste our time. Testing takes a lot of time. Even if we set up automated testing, we don't want duplicate tests in there, because as the software becomes huge, the number of tests is also going to increase. So we don't want to, we want to minimize the time that is spent on running the automated tests every time a new build happens. Then sometimes desk checking source code. So this is the reviews that we discussed, static analysis and reviews. That helps and reduces some of the testing time, because a lot of errors get caught in that static analysis just through reviews. Then we might have to create test harness. So this is that's basically writing drivers or stubs. This is especially needed for integration testing. Test harness is needed when, say, your unit depends on some other units for certain information, but those units haven't been developed yet. They're not ready. We don't have them yet. So in those situations, we might have to write these drivers and stubs to handle those other dependencies. Then we have to describe the test oracle, basically a strategy of how we're going to determine whether a test has passed or failed. So that strategy needs to be devised. And then we actually execute the test cases and re-execute them whenever a new build is made. Whenever some changes happen, the source code is built again, and we want to make sure we re-execute the test cases so that the new changes, we want to make sure that the new changes introduced are not affecting any of the previous test cases that already successfully passed. So that's called regression testing, to basically continue to re-execute tests, and that's why all of the test classes are put into a test suite to allow for this regression testing. And then compare the results of the test with the test oracle, and again this is automated as well. We'll look at JUnit, which does this automation, and it provides us a report of all the tests that succeeded and all of the tests that failed based on this comparison with the test oracle. So that's the process for unit testing, and our goal in the testing life cycle is to first do a thorough testing of individual units. It's done by the programmer themselves who designs and develops the unit before testing the overall system. So the idea is to reduce the number of bugs and reduce the number of issues found. So with that in mind, testing is done at every phase. At the static compile time, even while the code is being written, just through walkthroughs. Then as soon as you have an initial working unit, we run the tests, and then as any changes are being made, we rerun tests, and whenever new functionality or new objects are added, the new test cases are added to test those particular objects, and so on. So that's how we continue building, and then once multiple units are tested and ready, then we put those together as a subsystem, and then test the subsystem and then the interaction of the subsystems, which is discussed in integration testing in a follow-on video. So the tool that's used in order to do unit testing specifically for Java is called JUnit. It's basically a library that's provided that works with Eclipse or outside of Eclipse as well. So JUnit can be set up along with Eclipse in order to write and run unit tests. So basically the idea is to create test cases and fixtures. Fixtures are any kind of test objects that you need in order to do the testing. So we write these test classes, and then within that test methods and any text fixtures that are needed are created. And then test suites are basically a collection of various test classes, so that the automation is possible. And then there is a test runner. So all of this together forms the framework in order to do unit testing. So JUnit was written by Kent Beck and Eric Gama. So basically it was written with this test first idea in mind, like the test driven development, so wherein tests are written even before code, and that would allow for regression testing, as well as facilitates refactoring. Whenever refactoring is done, if all of our tests are already there, then you refactor and then just run your automated test suite. So that way we can be sure that the software is still working after the refactoring as well. So it's a very helpful tool, and JUnit is open source, so it's available at junit.org, and the current version is JUnit 5. So the Java, the framework for JUnit, basically it provides these standard classes. There's a test class, and from that are derived test case and test suite. So they inherit from the test class. So basically, and then there's a test produces a test result. So the way it works is, say there is a unit to be tested. So this is the unit that we just wrote, and it needs to be tested. So typically we come up with a concrete test case class, which is basically inherited from JUnit's test case. So it already has some methods: set up, tear down, and run test. So all of those are inherited by the concrete class. It just has to provide its own implementation for these if there is any customized implementation. So to show you how this exactly looks, let's use an example of say my custom list class. So say I wrote a list class to handle the list data structure, and the methods that I have in this class are I can add elements to the list, remove elements from the list, check if a particular item is in there, and then check the size of the list. So these are the 4 different methods in my unit, my list, that needs to be tested. So what I will do is write another test class called myListTestCase. And I'm going to use the JUnit framework in order to do this. So myListTestCase is a subclass of test case. So here we are using the UML notation. So it's a subclass of test case. So it inherits all of the data and behavior of test case, and then any other new methods that are specific to my list. So here's the unit under test, the unit that's being tested with the 4 methods. So I'm going to have setup, tear down, and run test. So these are the methods that are already there in test case. I have to provide implementation for them. Now in addition to that, I'm going to write the test methods. So I want to test add, and then I want to test remove. So those are the 2 test methods that I'm going to implement. Now I'm not including test contains and test size for a reason. The reason is that both contains and size will get tested as a part of add and remove. So they will get called when the add and remove functionality is called. So I'm not specifically writing a separate test case for test method for contains and size. So that's how JUnit testing is done, and then in another video we'll show how you use JUnit with Eclipse in order to write a test class of this kind. So some of the other JUnit features are it has both a textual and a GUI interface. The GUI interface makes it very easy to look at what's the status of your tests, how many failed, how many passed, and it also shows a stack trace. When a test fails, you can click on the failed one and it provides the details of the stack trace and where the error occurred and so on. So for those reporting purposes, it's great. It also integrates very well with some of the build tools like Maven, and it's useful for continuous integration, and it's great with for as a build and release management tool. So continuous integration is where the system is set up in such a way that whenever the new code is added, it gets built. When it gets built, automatically all of the tests are executed, and if there's any failures, the report is produced. And then once there's a successful build, it's automatically moved to the it's checked into the source repository, and once it's over there, it's automatically moved to the server, and you have a running product at all times. So that's the idea is to make this whole process, automate this whole process, and make it seamless for the developers, and then the idea is also that all of the tests are run before the release or before moving it onto a server. And then the test results can be advertised as a project report. That's a great way for the management or the project leads to look at the status of the project and what needs attention and so on. If a particular change was made by one of the developers and then that led to certain test cases failing, then it's easy to identify through these reports. It's easy to identify what changes caused the failure, and then who made those changes, and then get to performing the corresponding fixes. So now, in addition, so just like we have JUnit for Java, there's there's variants of the same for other kinds of platforms, like say for Python or for web applications. There's variants of the same kind of framework that's available for them in order to do the unit testing. So with that, I conclude this video on unit testing. In follow-on videos, we'll see how unit testing can be done using Eclipse and JUnit 5, and also we'll look at integration testing in a follow-on video. Thank you.